Hello everyone, we're going to go ahead and work through the problems assigned out of section 5.6. First we need to solve this for x. The log base 4 of 5x minus 1 is equal to 3. So if we convert this to an exponential, we get 5x minus 1 is equal to 4 cubed. 4 cubed is 64. If I add 1 to both sides, 5x equals 65, and dividing by 5 gives me x is equal to 13. Now let's just verify that the solution we found is properly in the domain of the original function. So up at top, we're taking the log base 4 of 5x minus 1. In other words, 5x minus 1 had better be positive. We can only take logarithms of positive numbers. Well, if x equals 13, 5x minus 1 is equal to 64, which is positive, no problem. So this is a solution and it is in the domain. Here, let's try to solve this. Now we have logarithms base 4 on both sides, okay? But I have multiplication by 2 on the left and a negative sign on the right. So let's bring those factors in. On the left, I have a factor of 2, and on the right, I have a factor of -1. So in other words, I have the log base 4 of 1 over 16. Now logarithmic functions are also 1 to 1. So if the log base 4 of x squared is the log base 4 of 1/16, well then x squared had better equal 1/16. If I take plus or minus square root, I get x is plus or minus 1/4. But let's check the domain. Okay, algebraically, we appear to have two solutions. So let's check that they are both in fact legitimate. Okay, now in the original expression, we're taking a log of 16, that's not a problem, that's just some number, but we're also taking a logarithm of x. Is x in the domain of this log base 4 function? Here, x is positive, yes it is, this is in the domain. So x equals 1/4 is a legitimate solution. But x equals minus 1/4 is negative, that is not in the domain. Back in our expression that we began with, you cannot let x equal minus 1/4. If I put that in here, you'll be taking the logarithm of -1/4, and that's not legitimate. So -1/4 wasn't actually a solution. There is only one solution to this equation, and it's positive 1/4. All right, we've got the sum of two logs on the left, so let's condense that as a single log of x times x plus 15. Now, in this book, logs without a base specified do refer to base 10, so this is a log base 10. So let's convert this into an exponential. 10 squared is equal to x times x plus 15. So 100 is equal to x squared plus 15x, or x squared plus 15x minus 100 is equal to 0. This factors as x plus 20 times x minus 5 equals 0, which suggests there are two solutions, x equals -20 and x equals 5. But let's check that they are both in the domain. Okay? Our original expression has two logarithms, so we need to check, is x positive and is x plus 15 positive? I need to make sure that when I make a choice of x, both of these logarithms exist. And here we see that no, if x is -20, neither of these is positive, so this isn't a solution because it isn't in the domain of the logarithms that form our original expression. X equals 5, however, yes, 5 is positive and 5 plus 15 is also positive. So this is a solution, it's the only one. Okay. Looking back at what happened, the first thing we did was we said the log of x plus the log of x plus 15 is equal to the log of this product. That's true as long as all of these logarithms exist. So if x is -20, here I have a negative value, that's bad. Here I have a negative value, that's bad. But if x and x plus 15 are both negative, then x times x15 is actually positive. So -20 is a solution here, but it is not a solution here because the individual logarithms wouldn't exist. Negative times negative equals positive, so here -20 is not a problem, but back here it would be. You cannot take the logarithm of a negative number. This is why when we finish solving these logarithmic problems, if we have done any steps like condensing logarithms together, we always check whatever values of x we find as solutions, we check that they are indeed solutions to the original expression. Moving on. So here we have log base 3 on the left added to another log base 3. Let's condense them. Let's convert this to an exponential. Okay, I can expand out the thing on the left. We get x squared plus 44x plus 315. And on the right, we get 27. Now, if I subtract 27 from both sides, x squared plus 44x, let's see, 315 minus 27. Well, 27 I can write as 15 plus 12, so I can take away the 15 quite easily. Then I have to take away another 12, so I have 288. Now the question becomes, does this factor reasonably? So 288, I'm actually just going to pause the video while I figure out this factoring. Okay, I paused, took a look. I was figuring this was going to factor quite readily into integers, and it doesn't. Our only option here really is, let's use the quadratic formula. So x will be equal to negative 44 plus or minus the square root of 44 squared minus 4 times 1 times 288, all divided by 2. Okay. Now, I'm just pulling out a calculator to go ahead and compute that discriminant of 44 squared minus 4 times 288 for a net result of 784. So this is equal to negative 44 plus or minus the square root of 784, all divided by 2. Now, rather than just get a calculator approximation, let's actually see if we can't simplify this radical. So 784 is divisible by 4. It's 4 times 1 and a 9 and a 6. 4 times 196. 196 is also divisible by 4, leaving behind 49. Okay, so 4 times 4 times 49 is 4 squared times 7 squared. So we have negative 44 plus or minus the square root of 4 squared times 7 squared all over 2. So negative 44 plus or minus 28 over 2. In other words, negative 22 plus or minus 14. Okay, so I'm going to come back over to the left here for our two solutions of negative 22 plus 14, which is negative 8, or negative 22 minus 14, which is negative 36. Okay, it's not that the quadratic formula was our only hope, it's just the numbers involved are a little large to attempt the factoring just in your head. Okay, I'm not so good at that sort of in your head integer factoring. So the quadratic formula is what I had to use, so why not show you that it is something that we can use whenever we need to. Okay, so we managed to solve this for x and got negative 8 and negative 36. But remember, we want to check, are the solutions both in the domain of the original expression? Now, what would be too easy to do is say both of these values of x are negative, and therefore they are not. Okay. However, if x equals negative 8, observe that x plus 9 is positive, as is x plus 35. In other words, even though x is negative, the thing that we take a logarithm of will be positive. So x equals negative 8 is a solution. Even though x is negative, we never actually take the logarithm of a negative number. However, if x equals negative 36, well then, x plus 9 is definitely negative. So that's not going to be a solution. Our only solution is x equals negative 8. All right, continuing forward. We want to solve this expression. We have two natural logs being added together. So let's go ahead and express that as a single logarithm, x times x plus 10. And on the right, we get 3. Okay. Now converting this to an exponential just gives me x times x plus 10 is equal to e cubed, which is not the most straightforward number, but it is just a number. So if I expand this out on the left, we get x squared plus 10x is equal to e cubed. I subtract the constant number e cubed. And now we have a quadratic that I really have no chance of factoring without the quadratic formula. So this, using the quadratic formula, we get x is equal to negative 10 plus or minus the square root of 10 squared minus 4 times 1 times negative e cubed all over 2. In other words, negative 10 plus or minus the square root of 100 plus 4e cubed all over 2. Okay, now there is our pair of solutions. However, we have two numbers here, negative 10 plus the square root of 100 plus 4e cubed over 2, and negative 10 minus the square root of the same thing. Note, okay, I'm going to address the one on the left first. So let me change colors just for clarity. 4e cubed, I don't know exactly what it is, but it's definitely positive. Therefore, 100 plus 4e cubed is definitely bigger than 100. So the square root of 100 plus 4e cubed is definitely bigger than 10. So this expression for x, negative 10 plus all that mess, I have negative 10 plus, while I don't know the value exactly, it's definitely bigger than 10. So this numerator is positive. I have a positive number over 2. X is positive. X is positive and x plus 10 is definitely positive. So this is a solution. It is in the domain of the original expression. However, okay, once we know that the square root of 100 plus 4e cubed is bigger than 10, if I was to subtract it, that would be less than minus 10. So this numerator is less than negative 20. Negative 20 over 2, that is definitely negative. This value of x, even without a calculator, I can tell this is negative. And if x is negative, it is not a solution of the original expression. Okay. So even without using a calculator, I know this won't be a solution, but this will. However, in this problem, we are instructed to express solutions in exact form, there it is, and as a rounded decimal. So if I quickly pull out a calculator and try to compute negative 10 plus the square root of 100 plus 4e cubed all over 2, about 13.61. Okay. All right, let's solve this. Very similar to the last problem. So we've got two logarithms base 6 on the left, so we combine them into a single logarithm. Thankfully, in this case, since our base is not e but an integer, when I convert this to an exponential expression, we do just get integers everywhere. Expanding on the left gives me x squared plus 9x plus 20, and on the right I get 36. So subtracting 36, x squared plus 9x minus 16 is equal to 0. Okay. Now, unfortunately, this does not factor with integers, but we can use the quadratic formula. Okay, so x is equal to negative 9 plus or minus the square root of 9 squared minus 4 times 1 times negative 16 all over 2. So negative 9 plus or minus the square root of 81 plus 64 all over 2, negative 9 plus or minus root 145 over 2. 145 does not have any obvious factors that I can think of. Let's see. I can't factor a 2 out. I cannot factor a 3 out. I can factor a 5 out, but not a 25, which means I'm not going to bother factoring that out of the radical. Let's see, it's not divisible by 7 or 11. No, this is just what it is. Okay. However, I do know that the square root of 145 is just a bit bigger than 12. This is barely larger than the square root of 144. In other words, negative 9 plus root 145 is going to be approximately 3, and negative 9 minus root 145 is going to be approximately negative 21. Okay. Specifically, and then I need to divide by 2, sorry. So if negative 9 plus root 145 is approximately 3, then x is approximately 3/2, and if negative 9 minus root 145 is approximately minus 21, then x is approximately negative 21/2. Okay, this is without a calculator. I'm just being close enough. Okay, it's not equal to 3, but it's going to be pretty close. X, here is going to be pretty close to 3/2. Point being, I want to check my domain. If x is positive 3/2, or at least quite close, both x plus 5 and x plus 4 will be positive. Okay, so I'm going to come back over here and check for whether the solutions we found are actually both in the domain of the expression we began with. If x is roughly equal to 3/2, then I am in the domain of both expressions. However, if x is pretty close to negative 21/2, I mean, that's pretty close to negative 10, negative 20/2. If x is roughly negative 21/2, both of these, x plus 5 and x minus 4, they'll both be negative. Which means the only actual solution was where I took the positive choice in the quadratic formula. Negative 9 plus the square root of 145 over 2. And again, we are specifically instructed to please round this off and give a decimal approximation, so I'll go ahead and do that. Negative 9 plus the square root of 145, all divided by 2. I thought this would be approximately equal to 3/2. Having plugged it into a calculator, it's approximately equal to 1.52, which is pretty close to 3 over 2, or 1.5. All right, let's solve this one right here. What I could do is I could convert this to a logarithm directly by saying x is the logarithm base 8 of 6. That's an exact answer. I mean, that works. But what is this approximately equal to? My calculator does not have a logarithm base 8 button. I mean, yours might, but mine doesn't. So rather than do this conversion, if 8 to the x equals 6, then the natural log of 8 to the x must equal the natural log of 6. I mean, if two numbers are the same, the left and right, 8 to the x and 6 are the same number, then when I plug them into the same function, I'll get the same result. So the natural log of the left must equal the natural log of the right. Based on properties of logarithms, however, this power of x can be factored out. Now I can divide by log 8, and now I have a nice exact expression. I don't need to check whether this is in the domain of the original, because here I have an exponential, and the domain of exponentials is all real numbers. So this is definitely a solution. If I wanted to get an approximate answer, well, sure, I just go ahead and punch into a calculator, what's the natural log of 6 divided by the natural log of 8, and I get approximately 0.86. Okay. So the fact that I don't really need logarithms of other bases. I can always express things through the change of base formula. Notice the change of base formula does say the logarithm base b of c can always be written as log base a of c over log base a of b, where a can be whatever you want. Specifically, if I use a to be the natural base, I can make this the natural log of c over the natural log of b. Okay. In a sense, you could have just used the change of base formula to go directly from this expression to this. But the change of base formula tells me I don't need to worry about bases in general. If I can just work with one chosen base, I can always convert into it. Okay. And as I mentioned earlier, scientists, engineers tend to work in base 10, mathematicians tend to work in base E. So I will always be converting things by default to the natural log. It's not incorrect to use another base, it's just not conventional. So let's go ahead and solve this. So I have the number on the left must be equal to the number on the right, which means if I take the natural log of the number on the left, it must equal the natural log of the number on the right. Now I can bring out powers as factors. Just be judicious with your parentheses here. Now what I want to do is I want to get every term that involves x to one side and every term that doesn't to the other. So let's distribute this thing on the left. So I get natural log of 6 minus 3x natural log of 6 equals x natural log 7. I'm going to go ahead and add 3x log 6 to both sides. So on the left, I now just have log 6, but on the right, I have x times the natural log of 7 plus 3x times the natural log of 6, from which I can factor out an x, log 7 plus 3 log 6. Now I can divide by log 7 plus 3 log 6 to obtain x is log 6 over log 7 plus 3 log 6. And since my original is just a couple of exponentials, I really don't need to check domain. All I did here was divide this over to this side, leaving behind just x. Okay, compare this to some of the earlier problems from this section where the only real technique was to express both 6 and 7 as powers of the same base. Now, with the power of logarithms at our disposal, we don't need to rely on such tricks. So here, okay, solve the following. 7 to the 2x plus 7 to the x minus 42 equals 0. You'd be forgiven for thinking, oh gosh, if I could just get them both equal to, if I could get everything on both sides equal to powers of 7, then I could use the fact that exponentials are 1 to 1. Maybe I want to take a logarithm. Unfortunately, if you hit either side with a logarithm, on the right, the log of 0 doesn't exist. And on the left, the logarithm of a sum does not break up in any reasonable way, so that's not really going to help. This is a pretty silly little problem. It just relies on noticing that 7 to the 2x is the same thing as 7 to the x squared. So what we really have is 7 to the x squared plus 7 to the x minus 42 is equal to 0. Let's just suppose that I replace all of my 7 to the x's with y's. Now I have y squared plus y minus 42 is equal to 0. That can be factored as y plus 7 times y minus 6 is equal to 0. In other words, y is negative 7 or y is equal to 6. Now we can go back and say, y wasn't just any variable, it was 7 to the x. 7 to the x equals negative 7, or 7 to the x equals 6. This first one here, however, I have an exponential function, 7 to the x, producing negative 7, but the range of 7 to the x is only positive numbers. So this has no solution. I cannot raise 7 to the x and get out a negative number. So the only solution is 7 to the x equals 7. And if I want to solve this for x, I'm going to take the natural log of both sides, bring down that power of x as a factor, and divide by log 7. So here is, in fact, the only solution. Okay. And the general technique of this sort of trick problem was just to notice that what we actually wanted to start off with was a quadratic expression by noticing that the 7 to the 2x can be rewritten as 7 to the x squared. We then solve that quadratic expression on its own before coming back to the exponential problem. The quadratic expression does have two solutions. However, 7 to the x can't be negative, so this value of y will never actually occur. The only value of y that will produce a 0 here is 6, for which x must be log 6 over log 7. Okay, the population of a country in 1995 was 284 million people. In addition, it was growing at a rate of 1.2% per year. Assuming that continues, we are given this function here to represent the population in year t. When will the population reach 306 million people? So the unknown is when, in other words, t. However, what we know is the population. Population. In other words, we know p of t. So for the first one, the known population is 306 million. Notice that the way this was given to us, p is already expressed in millions. So I don't need to put 306 million on the left. It's just 306 because the function is already expressed in quantities of millions. So 306 is 284 times 1.012 to the t minus 1995. So what I need to do is get t. The first thing I'm going to do is divide both sides by 284. Okay, these cancel off quite nicely. We're going to go ahead and just work with 2-digit decimal approximations for convenience rather than a whole bunch of fractions. So 306 over 284 is about 1.08. So this is 1.0. I'll actually carry 4 decimal points. 1.0775 is approximately 1.012 to the t minus 1995. Now if I take a natural log of both sides, we'll get that the natural log of 1.0775, which is approximately 0.0746, okay, now on the right-hand side, I'm going to take this exponent of t minus 1995 and bring it down as a factor. Natural log of 1.012. Now I'm going to divide natural log of 1.012 over to the other side. So 0.0746 over the natural log of 1.012 is approximately t minus 1995. I'm just going to go ahead and do that computation. Take this, divide it by the natural log of 1.012, 6.2548 is approximately t minus 1995, and now all I have to do is add 1995 to both sides to get t will be approximately, let's see, 1995 plus 6.25 is 2001.25 something or other. So the year in which the population will be 306 million people, it'll happen sometime in the year 2001, sometime in the spring of 2001. Okay, the only thing that changes for part B, for which I'm going to erase the entire slide just to start from the beginning, is the known population is now not 306 million, but 386 million. So we get 386 million is equal to 284 times 1.012 to the t minus 1995. So now let's not simplify using a calculator as we go. Okay, divide both sides by 284. So now I get 386 over 284 equals 1.012 to the t minus 1995. Take a natural log of both sides. So I get the natural log of 386 over 284 is equal to the natural log of 1.012 to the t minus 1995. Bring down that power as a factor. We could actually on the left break this up as a difference of two logarithms, but I'm not going to. Natural log of 386 over 284 equals t minus 1995 times the natural log of 1.012. Divide the natural log of 1.012. Natural log of 386 over 284, all divided by the natural log of 1.012, is equal to t minus 1995. And finally, add 1995. T is 1995 plus the natural log of 386 over 284, all divided by the natural log of 1.012. Now I have a nice exact expression. So if I really want, I can come back and compute this now and only introduce possible rounding errors at the very end rather than introducing a bunch of them along the way. So 1995 plus the natural log of 386 over 284, all divided by the natural log of 1.012, 2020.72. So in what year will the population reach 386 million? Somewhere in the fall of 2020. All right, the value of an automobile can be modeled by the following function. All we need to do is set these known values here and solve for t. Well, you know what? Let's just take it a step further and solve for t before plugging in any particular value, because then I can just plug in those things at the end and already have solved everything. The first thing we want to do is divide by 14,792. Take a natural log of both sides. And we hopefully see already that on the right-hand side, if I take a natural log of this, I'm going to bring down t as a factor. Then just divide by the natural log of 0.83, and we'll get t is given by the natural log of v of t over 14,792 over the natural log of 0.83. And now all we have to do for the various parts of the problem is say, well, what if the value is 7,000? Then t is the natural log of 7,000 over 14,792 over the natural log of 0.83. And since I've already done all the work, all I have to do is punch this into a calculator. So let me do so. Natural log of 7,000 over 14792, close parenthesis, divide by natural log 0.83, 4.02. Now for b, all I have to do, let me color code this so b will be in green. All I have to do is replace this 7,000 with a 6,000. But it's the same computation, and I end up quite quickly getting 4.84. And for part C, I replace the 6,000 with a 4,000. And since I already have it set up in a calculator over here, I'm just changing one digit and then asking it to recompute, 7.02. And this makes sense. Okay, if we were actually modeling the value of a car, we expect the value going down to correspond to the length of time going up.